recap the different ways we describe motion in physics, as we've considered some different approaches so far. Of course, any analysis of motion starts with some form of recording. And so far we've recorded times and distances manually over longer intervals and then developed more precision as we realized the limits these present. And the first of these more precise recordings we'll consider is the motion diagram. And the form of motion diagram we generate in our physics class is the ticker tape. Now remember, the basis of this diagram is the creation of marks, or ticks, at equal time intervals. Now this can be different from diagram to diagram, but our ticker tapes have dots generated every 1/60th of a second. So the time interval of 6 spaces is 0.1 seconds. And now we count out another 6 spaces to get 0.2 seconds, and then 0.3 seconds, and so on for the remainder of the recorded tape. Then we use a distance for those 6 spaces as our position information that we record in our second representation of motion, the data table. Now we recorded interval displacements, but we keep a running total here, as this will be the information we'll need to create our third representation of motion, the position time graph, which we denote dt with the harpoon over the d to represent the vector nature of displacement. And of course our third representation of motion is our velocity versus time graph, or vt. Again, note the vector nature of velocity.
But let's get back to the position time graph and explore the information we can glean from it.
Now remember, when dealing with straight line segments on position time graphs, we can determine the velocity from position and time by taking the slope of that segment. But we have to remember that this is the average value of velocity over the entire segment, and we haven't considered how the motion has changed over the interval, so we assume it's a constant value. So let's consider the slope of the straight line for the first 1.0 second time interval, which for our data has a value of 53.1 centimeters per second. And we derived this from the equation d2 minus d1 over t2 minus t1. And interestingly enough, when we apply the same formula with the displacement over the interval from 0.4 seconds to 0.6 seconds, we get roughly the same value, even though the velocities before and after the halfway point of 0.5 seconds are markedly different. Now if we keep taking the straight line segment and moving it down until it touches the graph at exactly the 0.5 second mark, and only the 0.5 second mark, the same slope as the two we've drawn above forms a tangent to the curve and has the same slope as the curve exhibits at exactly 0.5 seconds. The velocity described by this tangent is referred to as the instantaneous velocity, the velocity of the object at the instant where the straight line intersects with the curve. Interestingly enough, when we look at the data table where the position and time information have been used to calculate the speed at 0.5 seconds to be 54 centimeters per second, this only differs from the average value for the entire 1 second interval by under 2%. For calculations based on experimental data, this is pretty good agreement. And when we develop the conventional kinematics equations, or the equations of motion, it can be mathematically demonstrated that the average velocity of any interval of time is equal to the instantaneous velocity at the midpoint of the interval, provided the object is undergoing uniform acceleration, which should have been the case for this demo. Notice that we kept reducing the interval around 0.5 seconds to get to this instantaneous velocity. Newton had to develop new terminology to determine this mathematically when he recognized that this velocity could be calculated using the limit as the time interval approaches zero. Of course, this interval is in the denominator of the velocity expression and is precluded from ever reaching the value of zero. So the slope of the tangent is the instantaneous velocity at any point on the curve, and it can be demonstrated that the slope of tangents at different instants along this curving position time graph are increasing uniformly. This would suggest that the velocity of the object is also increasing uniformly, and this again is in good agreement with the velocity time curve generated from our data. But the information flows both ways. Just as the slope of a position time curve describes velocity, the area between a velocity time curve and the time axis also yields some interesting information. Let's look at the area of the trapezoid formed over the interval from 0 to 0.2 seconds. It can be demonstrated that this area will provide the displacement, or the change in position over this interval. The area of a trapezoid is the average value of the two heights multiplied by the base of the trapezoid. In our case, the two heights are v1 and v2, so half of this sum is the average velocity, and the base is the interval of time delta t. Now you'll see this equation again before this unit's finished, but for now we'll plug in the numbers we read from the graph over the 0.2 second interval, and we find a displacement of 4.8 centimeters. Note that the units are consistent with displacement, as centimeters divided by seconds times seconds yields a unit of centimeters. And if we go back up to the data table, we see that the displacement after 0.2 seconds was 4.8 centimeters. This can also be seen by reading the value from the position time curve at 0.2 seconds. Now this calculation is valid for any interval of time. For example, if we go back down to the velocity time curve and determine the area for the interval of 0.4 to 0.7 seconds, and using the same method as before, the area can be found to be 17.1 centimeters. And looking up at the data table, if we look at the difference in positions between 0.4 seconds and 0.7 seconds, the displacement is 17.3 centimeters. Now for a calculated value, based on estimated values from a graph, this again is agreement well within experimental expectations.